All right, this is what I came up with. So this is what we're going to do today. We're going to go through some chapter 1 questions. I tend to focus on the calculations. I've actually started to make up exam 1 already. And I've decided to stress fundamental calculations. That's what the majority of the exam is, okay? Making sure you are incredibly comfortable with the metric system, within the metric system, moving between the metric system, doing a temperature conversion, calculating moles. All of this is what the focus of the exam is going to be. Of course, we haven't covered chapter 2 yet. Okay, so this is all chapter 1 questions. Which step is not part of the scientific method? What do you think about this one? Say B as in boy, E as in Eric. Stop experimentation once the desired result is achieved. Do you agree? It's true, right? That's the one we want. Form a testable hypothesis, make observations, conduct probable experiments, identify different factors that affect results. This should be an easy question if you just read a little bit on the scientific method or you came to class and heard our discussion. So, any questions on this one? Okay, good. So, suppose it takes exactly 1 minute for your heart to circulate all 5.6 liters of the blood in your body. How fast does your heart pump this blood in cubic centimeters per second? Well, we're going to do it. I don't have the answers in front of me. You're going to have your calculators out to do it. But we're going to set it up and solve it. So, first of all, someone tell me what a cubic centimeter is equal to in a volume unit of liters. How many liters is a cubic centimeter? Who said that? What is it? 10 to the minus 3, right? Right. So 1 milliliter and 1 cubic centimeter are the same. And of course, a milliliter, as the young lady said, is 10 to the minus 3 liters. Wait for my mic. 10 to the minus 3 liters. Milli, remember, is 10 to the minus 3. So you can do this however your brain works the best, but we've got, let's just write what we have, 5.6 liters per minute, right? That's what we're told. Pumps 5.6 liters every minute. Times, doesn't matter if you do the numerator first, the denominator, we have to convert both. We have to get 1 to seconds, the bottom 1 to seconds, top 1 to milliliters, right? Is that what we're asked? Cubic centimeters per second. So 1,000, if you want to do it like this, 1,000 milliliters. See, I've already done it wrong. Why do I know I've done it wrong? Right, we're not canceling out. I'm going to wind up with liters squared over milliliters, which is nonsense. So let's erase that. So we've got 1 liter down here, and you can do 1,000 milliliters like this, or you could have done it like this. 10 to the minus 3 liters in 1 milliliter. That gets you the same answer, right? That's using the prefixes if you're more comfortable with that. I tend to do it this way. My brain works a little bit better, and most people do, thinking about that rather than negative exponents. But those give you the same answer because dividing by 10 to the minus 3 is the same thing as multiplying by 1,000, right? Just keep in mind that the prefix always goes with the base unit. And you'll see that in one of my other examples. And then what I mean by that is we say that 1 milliliter equals 10 to the minus 3 liters. These are on opposite sides of the equation. The milli and the 10 to the minus 3, those are what make them equals. They have to be on opposite sides. What you don't want to do is say 10 to the minus 3 milliliters equals 1 liter. That's wrong, right? You see what I'm saying? The milli and the 10 to the minus 3 are on the same side, and you've got opposite sides. That's a common mistake students make when they get confused with the metric system. You need to get comfortable with this. So looking at our units, we've got rid of liters, so we're good. We're now at milliliters per minute, but the question asks for seconds. So we still need to go to seconds, and that should be pretty straightforward. 60 seconds per minute. We want seconds in the denominator. That'll get rid of my minutes. And then if we do the math, which one do we get? C? Everybody agree that we get? Put in your gut confirmation and more than one calculator. Okay, so everybody see what we did? Dimensional analysis. Just move across from liters per minute, converted to one of those first, seconds or milliliters. And then remember, since this is the case, we don't have to really do it. You could do this, but you don't need to do this on a multiple choice exam. 1 cubic centimeter per 1 milliliter. You don't need to even do it on a written exam. We have to solve it. That's people just know that, accept it. You don't have to show it. 1 milliliter is 1 cubic centimeter. Questions on this problem?
Someone had said it in the chat, but are we getting a conversion factor? Like, because I didn't know 1 milliliter from 1 cubic centimeter.
That you will, yeah, that you will not get. Okay, you're expected to know the metric system. What you will get is 2.2 pounds in a kilogram, 0.62 miles in a kilometer, those types of conversions. But no, you should know that 1 cubic centimeter equals 1 mil, and therefore 1,000 mils in a liter. Okay, so keep in mind it's open book, open note, the exams. So theoretically, you don't have to memorize. You will realize, though, that your final exam is not open book, open note. And that is the common final that everyone's taking. You'll have a sheet with equations and some conversion factors and even solubility guidelines and stuff like that, but it will not be open book, open note. That's why I suggested to you to make up a sheet. Like I said, flipping through your book during an exam will just wind up causing you to run out of time anyway. So you should know off the top of your head, 1,000 milliliters equals a liter and 1 cubic centimeter equals a milliliter. If you're going through your book saying, oh, heck, what's a cubic centimeter? Is that equal? You're done. Okay? You just can't be doing that. Okay? And for those of you that are foreigners that come from another country, then more likely than not, you already know the metric system. Okay, us in Britain are one of the few countries that still use this standard British US system. Even the Brits use a lot more of the metric system now. All right, so the next one. A single strand of silk may be as long as 4 times 10 to the 3rd meters. What is the length in miles? So there you see it where I've given you the conversion factor. I'm not expecting you to know that. I used to tell my students it's always nice to know one bridge, what I call a bridge, and that is a distance bridge, a volume bridge, and a mass bridge, because then you can do any conversion at any time. Okay, I can convert anything to anything at any time because I know some bridges without having to Google it or whatever. I know a distance one, I know a volume one, and I know a mass one. And even if the bridge I learned is very different than what they're asking, I can always convert within the US system and the metric system and get to that bridge. But in this case, you've got 1 kilometer, 0.6214 miles. All we have to do is convert meters to kilometers and then kilometers to miles. That's all. So knowing the metric system, you should know the meter to kilometer conversion. And what's this going to look like here? Let's get to kilometers. Let's get from meters to kilometers first. 1 kilometer equals 1,000 meters. So we're going to want the meters in the denominator, right? Once again, you could have done 10 to the minus 3 meters in a kilometer, something like that. But most students over the years I've talked to tend to like to do it this way better. I think our brains just work better than working with negative exponents. So that's good because that gets rid of meters, gets us to kilometers, and then we got the second conversion factor. We want miles in the numerator. Looking at dimensional analysis, we look good. We got rid of meters, we got rid of kilometers. Let me double check what the question's asking. Length in miles, good. That's what I'm going to get. My answer in miles, and which one do we get? D as in dog? Thank you. 2.5 miles. It's not too bad, right? Okay, so this is what I mean when I was going to stress fundamental conversions, fundamental math. So I'm not going to give you a lot of real difficult. There's a couple difficult. I've started to make up the exam already. It's a couple difficult calculations designed to find my A students. And just in general, the time of the exam, it's only 25 questions usually. My A students will show up. But I'm not, this is not difficult material, okay? This is the easiest material. Chapter 1 and 2, it really is. It's the stuff that a lot of you have had in high school. So it's a good chance to do good on an exam and get off to a good start. You have to put the time in. Get to the point where you're comfortable with working through, a half a dozen problems in like 20 minutes. Good on this one? Hot air balloon is filled with 1.03 times 10 to the 6 liters of air. Density is 1.20 grams per liter. Air is about 1,000 times less dense than water. As the air in the balloon is heated, it expands. Of course, we'll learn that. If you didn't know it already, most of you know that. We'll learn that in the gas law chapter. I think it's chapter 9. Expands so the volume decreases. I'm sorry, expands so the volume increases. What is the density of the heated air in the balloon? The density should decrease, right? You've got the same numbers of molecules spread out in a larger volume. Okay, what do I do? Someone tell me, don't say multiply it. Someone tell me logically in words how I'm going to solve this. For the second density, right? So we're given the volumes of the two. Okay, so we've got the hot air balloon. It's got this volume and density, right? So we've got, ultimately, and we got a second density. So we got these D1s and D2s here. We got two densities. And theoretically, right? So we've got this volume and density. We can simply calculate the new density if we get the mass of the material that's in the balloon, right? Because the mass of the air molecules is not changing. All we're doing is expanding the volume, so the mass is the same. So if we calculate the mass, we can then divide it by the new volume and have the new density. The mass is what's constant, right? The volume and the density are what is changing. And the density will change proportionally to the volume. So since we have 1.03 times 10 to the 6 liters. Okay, so now we want the mass. If we just take that density and we can do 1.20, did it wrong again, caught myself. I'm going to wind up with the wrong units. 1.20 grams per liter. That will give me the mass of the air in that balloon, right? See, my volumes are canceling out. I'm left with mass. And then once I take my mass there and divide it by the new volume, I'll have the new density, and that'll be my answer. So what do I get there first? mean, whatever. Yeah.
Or 1,236,000 or
1.236. 1.236. I'll just take an extra sig fig with me times 10 to the sixth, right? And that is grams. Someone else got this? Okay. So we got confirmation. That's the mass. I didn't round off now. I'm only supposed to have 3 sig figs, but I like to take extra digits through my calculation so I don't wind up with rounding errors. And now simply I've got 1.236 times 10 to the 6 grams divided by 1.12 times 10 to the 6 liters. And we probably get B, I'm just guessing, but that's the one that looks the most logical, obviously. You can just process of elimination. You could have probably looked at these answers and figured out what, it was going to be either A or B, right? Did you get B? Yes? B's our correct answer. You know the density's got to decrease, right? So make sure you get the right, think about, that's that coast thing. Think about your answer. Got to decrease, so it's got to be either A or B. Questions? We good? All right. Good to hear. Which of the following does not show a correct relationship between units? E as in Eric? E is correct. It's backwards, right? It should have been 10 to the minus 6 liters per microliter for 1 microliter, right? So remember what I told you. Scroll there. Remember what I told you, you want those on the opposite sides of the equation, the micro and the 10 to the minus 6. This one's right. These are written, with the 1,000 grams per kilogram, 10 to minus 3 seconds in milli. So on opposite sides, that's correct. 10 to minus 9 meters is 1 nanometer. That's correct. Opposite sides, and that's the right prefix. Nanos 10 to minus 9. 1,000 milligrams in a gram, correct. This is the correct answer because it's the wrong one. To correct it, it should have been 1 microliter is equal to 10 to minus 6 liters, or 10 to the 6 microliters equals 1 liter, not 10 to minus 6 microliters, right? That's where you got to get comfortable with the metric system. And that's where the prefixes do come in handy, realizing they have to be on opposite sides. Micro is over here, and that's what's equal to 10 to minus 6. You put them on opposite sides. Micro equals 10 to the minus 6. Questions? All right. What value should be reported as the volume of a strip of aluminum foil measured 15.37 centimeters by 42.5 centimeters by 0.0010 centimeters? And the second part I added, there's no multiple choice for that. We'll do that afterwards. We'll convert it to 2.2 inches, cubic inches. But let's do the first part. Obviously, the calculations are all the same, so it's a matter of significant figures. I don't consider this, by the way, a calculation problem. When I say the exam's roughly half calculations, about 13 calculations. I don't consider this a calculation because you all learned addition, subtraction, multiplication, division in elementary school, whatever, middle school. Maybe with, well, that's elementary, I guess. So this I consider just a fundamental concept, significant figures. And what's my answer going to be? D as in dog, right? We only want two sig figs, right? Why? This has two sig figs. That 0 after the 1 is significant. But the ones before are not. They're just placeholders. And the rule for multiplication and division, the weakest link principle here is the one with the fewest significant figures. Therefore, we want 2. So D as in dog is correct. Now, the example I was trying to come up with the other day, I think Megan was laughing at me because I couldn't think of an example, but here's the one I was looking for. The reason why we don't use the same rule for addition and subtraction. Let's say we were adding up all these numbers. 32.6947 plus 1.312 plus 0.006. When you add these all up, you get 34.0127. If we use the multiplication and division rule, how would we report this number? 30 or 3 times 10 to the first, right? 1 sig fig. You lose all that precision. But with the rule now, it's you truncate it, right? With the least number of decimal places, you now get to report all of this. And that's what you want, right? Okay, because you're just adding this, you know these are not significant, but you know they're zeros. They can't be anything but zeros, right? What comes after that 6, and that 6 is uncertain, but those zeros are still zeros. They're not like they're possibly 1 there or 2. So you don't want to lose all that precision. That's why this rule for addition and subtraction is truncated. And that's what you see in the next example there. Very similar to the one I just did. So in this case, you wind up with like 35.7 something, right? But we got to truncate it after that 32, right? If you line it up like this, it's easier. You add that all up, you've got to truncate it here. So therefore you'll have, 35 point, but whatever. So it's, you don't even need to do the math. It's 2 sig fig, right? Everybody see that? Questions? Okay. Say that again.
Was this sig figs one of the questions that threw most people off on the quiz?
No, the one that threw off is the one that I talked about. I forget what it was now. The molecules and compound definition. So that's one. So there might have been, might have been 40% of the class that got it right, but I look for the ones at which only a third of the class got correct. Those are the ones I consider, gave most people trouble. We good on this though? Okay. I'm a baseball fan, so let's do a baseball calculation. A baseball has a diameter of 7.4 centimeters. Oh, wait, we never finished that one where we're supposed to convert to cubic centimeters. Here it is. Let's do this. Okay. This is important because I'm going to show you, because I actually got a question from someone that was working on smart work about this. So here we have 0.65 cubic centimeters, right? Times 2.54 centimeters per 1 inch, right? Am I done? Is that correct? No, a lot of you are shaking your head no, because look at my units. I wind up with centimeters, squared inches, which makes absolutely no sense. You've got to cube your conversion factor. Because keep in mind, think about what you're doing. You got to convert the length, the width, and the depth, or the height, whatever you want to call them. 3 times you got to do the conversion. So that's the whole point of the cube, right? You got to convert it 3 times. So this has to be cubed. That means my 2.54 is going to be cubed. So when I divide, so that's going to give you a very different number. And you can do the math. I don't know what the answer is, but now you've got cubic inches here. Cubic centimeters cancel out. And you have 0.65 divided by 2.54 cubed. What do you get? Megan, did you get it?
I did.
What'd you get?
I got 0.03986.
Someone else get that? Yeah. Now, I'm going to tell you a trick too with your calculator. What you're going to want to do for these exponential notations, the best way to do these. Andrew's going to lend me his calculator. So, oh, I can actually show it to you. Okay, it's going to be a little tough just with that light. Let's see. Let's see that screen. But I'm going to show you the buttons anyway. So, why is that? Oh, this is old Jack. What is this? This thing is very efficient. Okay, so when you do exponential notation, and don't ask me for an example because I'm going to forget how to come up with one, but there are times in which if you do this, let's do 3.5 times 10 hat 3. Okay, if you do that, you will run into problems with certain calculations. And that is when you have order of operations. And now what that sees that as is 3.5 is one number. Then you're multiplying by 10 to the third, another number. And if you've got division in there and order of operations, it will mess you up in certain calculations. The way to do it is this way. 3.5 second EE. That means times 10 to this, so it's actually a shorter, it's actually less key pressing. Second E, whatever you're, -3, 10 to the third. Always use that way. That treats that as one number. It will not affect you with order of operations. That does not see that as times, that is one number. Okay, so get in the habit of doing that anytime you're entering exponential notation. It's actually one keystroke less, so it's quicker, and it'll keep you from getting into problems. Question. There's only a few cases where that's an issue. But there will be cases like that. So, yeah, do that and get comfortable with it. Questions? Okay, now we're up to the baseball. Baseball has a diameter of 7.4 centimeters. Yeah. Oh, thanks. Baseball has a diameter of about 2.9 inches, whereas a carbon atom has a diameter of about 140 picometers or picometers. How many times larger is the baseball than the carbon atom? So what do we do? Anybody? We've got to do a conversion, but what mathematically, how are we going to figure out how many times bigger the baseball is? Division, right? You divide both the larger one by the smaller one, right? Anytime you're asked how much heavier is this dog than this dog, well, you take the the heavier dog and divide it by the lighter dog, whatever you're doing, distance, man. So we got to divide them, and then we got to do the conversion. So it doesn't matter which one you convert, whichever one you're comfortable with. So the way I would do this, and that's not necessarily the way you're going to do it, but the only way that I do it is the way I do it. So 7 point, actually I could do it, we could do it both ways. I don't necessarily have a preference, but 7.4 centimeters, okay? And now pico is 10 to the minus 12, right? Centis 10 to the minus 2. So a difference of 10, right? Okay, so we can do 140. And since pico is a smaller unit, we can say times 10 to the minus 10 centimeters. That'll work, or you could have done it with the numerator changed, right? Either way. And you would have had 7.4 times 10 to the 10 picometers over 140 picometers. So you're going to get the same answer. Whichever one you feel more comfortable with. But realize pico's 10 to the minus 12, centis 10 to the minus 2. So therefore, a difference of a factor of 10 to the 10. And what do we get? B? No. We won't get B. We'll get C. Oh, right, because you're dividing by 140, right? Factor of 2. Yeah, so C you'll get. Just keep in mind, this is 10 to the second right here, 1.4 times 10 to the second. So basically, you're dividing by 10 to the minus 8. So your answer should be 10 to the 8. Questions? You can go.
My brain comprehensive. Can you get them both in meters?
Yes.
And then do it that way.
Yes. You get that. Then that's what a lot of people are going to do until they get comfortable, get them both in meters. You know, because you've got these prefixes to convert them both to meters. It's an extra step, but no big deal. If you feel comfortable doing that, that's the most important thing. The shortest way is not always, necessarily the most comfortable way for someone. And it's not that big of a deal. Other questions? I was just explaining that because this is a factor of 2 right here. So this is really 1.4 times 10 to the second. That's why I originally thought, the answer was going to be B. And then I said, oh, wait, yeah. Yeah, so a lot of these, you can look at it and just kind of deduce what the answer is without even using a calculator. Next one should be pretty easy. If not, you've got some work to do. Calculate the diameter of a carbon atom. Well, actually, they're all different units, so it's not that straightforward. I thought it was just putting it scientific notation, but you've got to watch the unit too, right? So let's count this. I can barely see anymore. I got to change my prescription. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 3.4 times 10 to the minus 10 meters, right? That's not one of my choices, though. So, which one is it? It's going to be a little tricky, actually. You really got to be comfortable with your metric system. E is correct. E is an error. E is an excellent. That's the correct answer. So keep in mind, smaller unit, pico, right? Then meter. So the number's going to get larger. by a factor of 12. You move, so there it is, factor of 12. Effectively, it's 340 times 10 to the minus 10 picometers. I'm sorry, 10 to the 2 picometers, or 3.4. Effectively, it's 340 picometers, or 3.4 times 10 to the second. I don't know what I was trying to say there. Kilo is a factor of 3 different, right? And they're only a factor of 2 different there, so it can't be kilo. Centi is a factor of 2, but the number got smaller. It should get larger, right? So it should have been 3.4 times 10 to the 8th centimeters, not 10 to the 12, right? Nano is a factor of 1 different, so that's no good. This is a factor of 2. Nano again. No, oh, that's milli. I'm sorry, that's milli. Milli's only a factor of 3 different. That's way off. Well, no, it's not way off. It's off by 1. This one's off. So that should be 0.34 nanometers. Right? Because it'd be times 10 to the 9, you'd have 3.4 times 10 to the 1 nanometers, not 10 to the 0. So E is the correct answer. That's a good way to study, is look at all of these and correct them, if you will. You know, what would be the correct answer if it was in kilometers? What would be the correct answer if it was in centimeters? And when you get to that, then you know you're pretty comfortable with the metric system. Good? Questions? A student conducts repeated trials. So this is that precision one the student had asked me on smart work, I think it was. It's not the same one as the one that was on smart work, but similar. The one on smart work, I went back to look at it. They showed you 2 graphs, and that's the key. Sometimes it's tough to tell. Well, is that precise? I mean, you know, they're not exact, but they're off. You know, how do you know when? That's usually will give you enough information to kind of like deduce something along those lines. And now here, let's see. Repeated density of a sample of seawater, 1.3, 1.3, 1.3, 1.3. Those are all pretty close. You got 1.321, 1.323, 21, and 19. Those are all pretty darn close. They're all the same to 2 significant figures, the 1 decimal place. And then 3 of them have 1.32, and the other one is 1.31, but it's 19, right? It's very close to 2. So these are pretty precise. Okay. But the range is 1.02 to 1.09, so they're not particularly accurate. They're way off. So where's that? Inaccurate but precise, right? And then I think the one in the book, in the back of the book that I assigned, it's got 2 graphs. It's very similar. It's the same graph data as the one on SmartWork, but the question's different. And I'll show it to you, because here, at least they're showing you 2 sets of data. So it allows you to at least make a conclusion, hey, that the one is precise, the other one's not particularly precise, because they're showing you. Here it is here. This is the same data that was on SmartWork, and it's also an assigned question in the back of the book. This one here at the bottom, I have trouble. This one right here. What to do with this thing here? This one right here. Now they're showing you here. So this one's precise. They're not off by that much. You see. But this one, they're a little bit more scattered. So we definitely say this is more precise than that. Given this alone, you might be like, well, I don't know, is that precise or not? You know, it's a little bit tough to make that decision sometimes. So try to give you questions that it really depends on, you know, if it's a student measuring on one of these top loading balances, or someone using a super high precision scale to determine whether they're precise or not, because that top loading scale has a lot more error associated with it in general. Okay, so you could sometimes need more information than just be given like one of these and say, is that precise or not, you know? So try to avoid those types of questions on exams and quizzes. But here you're comparing, so that helps. All right, last question, I believe. Yes. Before I forget, your quiz 2 is due tomorrow morning, Thursday morning by 8 o'clock, right? Or 9, whatever the date, I think. On the outline, well, let me finish this and I'll do that. Then I can pull up the outline. I just don't want to forget, that's why. Okay. The distance between two hydrogen atoms in a water molecule is about 1.355 times 10 to the minus 10 meters. This again is very similar to the previous one. This is equal to what? Who said that? D as in dog, correct, right? Times 10 to the 9, right? Nanometers per meter is going to give you 10 to the minus 1. That is 10 to the minus 1. That's the correct answer. Yes.
So it's one of those things that like, I'm
Oh,
struggling.
there you are.
Sorry, I'm struggling to understand this question.
Yeah.
But is it one of those things that like you just need to look at the metric system, like the density and all that, and just kind of look, okay, say, okay, what's the difference between a meter at this point and then what's like a nanometer?
Yes, exactly. So you got to go through, and this can take a little bit of time. That's why if you get more and more comfortable with the metric system, it goes quicker. But basically, if you look at this, there's 10 to the 9 nanometers per meter, right? Is this meters I'm in here? Yes. So you'll wind up with 10 to the minus 1. So 1.335 times 10 to the minus 1 is 0.11335, right? Get that? Yeah. Do any of the others, you'll get something off. So if we did pico, it'd be times 10 to the minus 12. You'd get 1.355 times 10 to the second, which is going to be 135, not right? Not 13.5. That's what you have to do. Yes. Oh, no, it doesn't have to be. I make mistakes. These are actually pulled from this. Where'd this come from? No, this was, anyway, I can't remember. But let's take a look. A, millimeters. So we've got factor of 3. Oh, that's correct, right? 10 to the third. No, third. No, it should be 10 to the minus 7, not 10 to the minus 8, right? So you've got 1.355 times 10 to the minus 10 meters times 1,000 millimeters per meter. So a factor of 3. So this will be 10 to the minus 7 to make that correct. I thought you were right for a second there. Yeah, these are tough. They're not easy, and it really means comfortable with the metric system.